So I'm going to introduce you to Jesu Espino. Where have you come from to be with us?
Sorry?
Where have you come from to be with us?
I come from Madrid.
So this gentleman has come from Madrid to speak to you today, so thank you very much to Jesus for that. He's going to be talking to us about understanding the Go runtime, and we've got an almost full house, so fantastic. You've obviously chosen the right room to attend. Thank you so much.
Well, hello everybody. I'm going to talk about the understanding the Go runtime. This talk is a kind of continuation from another talk that I did the last year here in GopherCon UK that was understanding the Go compiler. It's not important that you've seen that previous talk. It's not going to be needed. I'm going to talk a bit about the compiler, but it's not that relevant for the talk to understand the internal process of the compiler. So let me introduce myself a bit. I'm Jesus Espino. I work for Mattermost. For whoever doesn't know, it's an open source alternative to Slack, a communication platform. But why I'm sharing that information? Basically because I'm a software engineer, a full stack developer. I write APIs and React applications and things like that. So that's what I do. So I'm not a Go runtime developer. Actually, I think there's a Go runtime developer, an actual Go runtime developer in the audience. So that's going to be a bit uncomfortable. But well, all these things that you are going to see in this talk are my learnings from reading the Go source code. So, yeah. The Go runtime version that I'm going to be talking about is the 1.22. This is relevant because we are going to see some concepts and some things that applies to this specific version. And more specifically, I have some slides where you are going to see at the bottom right corner the file name and the line number for that concept or where is implemented that thing. So if you want to do some homework, you can go to the Go runtime code for the version 1.22, and you are going to find that files and that line numbers, and the implementation is going to be there. So just in case you want to go deeper in some of the concepts that we are going to see here. Well, let me introduce a bit about the compiler. All the thing that you need to know about the compiler is how the compiler works in general. And the general behavior of the compiler is kind of like this. You have a Go program, you give it to the compiler does a magic trick, and suddenly you have a super fast binary executable. That's all you need to know. The Go compiler is magic, it's a great compiler, actually, and works really fast, really well. And it provides us with a ultra-fast ultra-fast binary file. So that's what is happening. It's converting source code into fast executable binaries. But how fast are that executables? Well, I did want to play around with that, and I want to compare Go binaries with C binaries, for example. So I write two implementations here. One is a Go implementation of an empty main function, so it's going to do nothing. And in the other side, we have a C implementation of an empty main function that is going to do nothing. If you compile and execute that, what you are going to get is that the Go file generated is 1.2 megabytes, and it's going to take 1 second to execute 1,000 times. What is fast is it's pretty fast, to be honest. But in the C side, you have 16 kilobytes and a third of a second to execute 1,000 times. So Go is taking 75 times more space and 3 times more execution times for doing nothing. What is kind of weird, right? The reason is this competition was rigged up front, so it's, of course, that's not fair because we are not comparing the same thing. We are comparing Go that has a runtime that needs to be initialized and needs to prepare the ground for executing your code, and C doesn't have that runtime. So, well, the compiler and the runtime works together. I'm going to show you here that we have that the runtime and the compiler works in tandem. What I mean with that is the compiler is going to take your code, compile that, take the runtime, compile that, and put everything together in the single binary. And it's going to take advantage of that because the compiler knows that the runtime is there. Let's see hello world example. If you compile a hello world like this, what you get is something similar to this. The top left corner in green is your code. And the rest of the block there is the runtime. So that's how it works, how the compiler is going to generate your hello world binary. This is, okay. This is this way because you have a hello world that is a very, very, very tiny program. If you have a bigger program, of course, it's going to your program is going to keep growing and the runtime is going to keep the same. So you eventually reach the point where the Go runtime is not that big in comparison to your code. So this is an exaggerated situation. But also, whenever you compile that, what you get is you get binary code, but that binary code matches perfectly fine with this assembly code. I don't want you to understand this assembly code. This is the assembly code generated for the hello world, but I don't care if you understand or not that because it's not important for what I want to convey. I want you to pay attention to these two lines here. These two lines are using a call instruction. A call instruction in assembly is saying, hey, just call this function. That's what it's saying. And you can see the first one is fmt fprintln. That is a function from the fmt package. Nothing very exciting there. But the second one is the interesting one. The second one is calling something in the runtime. It's calling more stack, no context. That is for growing the stack of the goroutine if it's needed, but that is put there by the compiler, knowing that the Go runtime is going to be there. It's not the only thing that the compiler leverage for that. Let's see some example of things that the compiler leverage from the runtime to give you syntax and give you some features. For example, if I compile this and filter only the call instructions, I'm going to get this here. If I check this line here, it's an append to a slice, and what I'm going to see is that the compiler is generating a call instruction for grow slice that is going to check if the slice needs to grow and grow the slice accordingly. This one is generating a new map. This new map has two keys, two string keys. So the first thing that it's going to do is call this run32. That is done because it's needed for initializing the seed of the map that is going to be used for the hashes, not the seed, the key for the map that is going to be used for generate the hashes. That is used for ensuring that the maps are completely in random order from one map to another. And after that, it's going to use another function from the runtime that is map assign fast string. It's using it 2 times because I'm assigning two keys. The next line is another assignation from the map, so another map assign fast string. So all this syntax that you see here is generating calls to the runtime instead of generating assembly code directly. Generate a channel is going to call make chan. Sending things to a channel is going to use chan send one. And iterating over a map is going to generate a map either init and map either next calls there. So that is when I say that the compiler and the runtime is tandem, that is what I'm trying to convey, is the idea of the compiler knows that the runtime is there, so the compiler is going to generate some call instructions instead of generating the whole assembly code for that. So the runtime. As I said, the runtime is included in your binaries, and the runtime is the first thing that is going to run in your binaries. I know that normally people say the first thing that runs in your binary is your main function. That's not true by far. So if you go, for example, and go and use readelf to get the information from the binary file, the elf file that is generated, you are going to get that the entry point points to some address. That if you use GDB to get that entry point, what you are going to see is that the entry point of your binary is not your main function for sure, is the RT0 Linux AMD 64.s. Well, that's the case for my computer. That is Linux and AMD 64. It depends on your operating system and your architecture, but in any case, it's going to end up in a file similar to that in assembly code. The Go runtime is writing mainly in Go, but there's some assembly like this for certain specific cases. But well, that is the entry point. And the entry point is going to go through all this process. Don't pay too much attention now to the whole process, because we are going to see this slide over and over again. We are going to go through all this process, all the Bootstrap process of the runtime. But well, the first thing that is going to happen is we hit that assembly code, and it's going to start running the Bootstrap process. One of the first things that happens is initializing the TLS, the thread local storage, for storing information specifically for the thread. Then it's going to jump into the sysargs. The sysargs is going to initialize something that comes from the operating system that is called the auxv. It's a vector of information that contains the arguments that you pass to your executable, the environment variables, and some flags. And also is operating system dependent. So this is going to have code that is specific to your operating system. The OS is going to initialize operating system related stuff, like the number of CPUs detected and the size of the huge pages. And if you have SIGO enabled, it's going to adjust certain signals. Then it's going to jump into the scheduler. The scheduler is going to be a big chunk of the initialization process of the runtime. The reason for that is because the scheduler is going to trigger other initializations. It's part of the scheduler initialization process. It's going to contain other initializations. It goes from the stop the world there to the start the world in the fourth line. So we are going to go through all the process, but everything that is going to happen there is related to the scheduler initialization. But let me talk a bit about the scheduler to give you some context for later. Whenever you see certain initializations, you have more understanding of what is going on. So the scheduler is kind of like this. You have different structures. One of them is the P structure, for example, that is the processor. It's a virtual CPU, and it represents a virtual CPU. A virtual CPU is going to be matching the number of virtual CPUs is going to be matching the number of cores in your machine, or the GoMax procs environment variable. It depends if you have configured it manually, but that's the number of Ps, the number of virtual processors. Then you have the Ms that are representations of the operating system threads. And can be the number of CPUs, can be more. It's not bounded there. The other thing that you are going to see is the Gs, the goroutines, that are going to be associated to processors. If they are running, they are associated to the processor and the Ms. If they are waiting to be run, they are associated to the queue in the processors, things like that. Also, you have the scheduler that is the SCED struct that is going to contain all the idle P's, all the idle M's, and goroutines that are waiting to be executed, and goroutines that are ready to be reused just in case you need a new goroutine. You can reuse some of them. Also, there's 3 global variables, global for the runtime, so they are global variables that contains all the M's, all the P's, and all the goroutines. And we are going to initialize all that stuff. Well, the first step is stop the world. Stop the world is a concept that is very common in garbage collector that basically means stop everything else and let's do everything serially without concurrency that can generate race conditions and things like that. So stop the world is the first step to ensure that everything goes smoothly during the initialization. Then we initialize the stack spools. The stack spools is a global structure that caches it's a cache for stacks, for goroutine stacks. So it's going to have different caches, one for 2K stacks, 4K stacks, 8K stacks, and 16K stacks. That's for Linux. In different operating systems, the different caches can be different. Also can cache bigger stacks. And at this point, we are only initializing the structure, but we are not storing any stacks for now. The next step is initializing the memory allocator. The memory allocator is responsible for requesting memory to the operating system and managing that memory. Let me show an example of how you can get affected by the memory allocator. These are 2 benchmarks. One is generating a slice of 124 integers. That means 8 kilobytes. That means 8,192 bytes. And you can see that the number of allocations per iteration is 1, and the number of bytes are exactly that, 8,192. On the other hand, I did exactly the same, but this time with 1,025. That's 1 integer more, that's 8 bytes more. So my expectation is now I'm going to need 8,200 bytes. I run the benchmark, I got 1 allocation per iteration, and what I see there is 9,472. So what? Why this random number? So that's because the memory allocator. So let's get a bit deeper in the memory allocator and what it does. The memory allocator, let's explain from bottom up. The memory allocator uses pages, memory pages. That is the one that the memory allocator is going to ask for the operating system for that pages of memory, for memory to use in the system. Then what you have is all these pages are grouped into MSPANs. MSPANs are chunks of memory that you are using to store variables of the same size. So an MSPAN of 8 bytes is going to store variables that are 8 bytes. And there are different sizes for MSPANs, 8 bytes, 16 bytes, 24 bytes, 32 bytes, 48 bytes, 64 bytes, 80 bytes. It keeps growing and keeps and the gap between them keeps growing too. And the biggest MSPAN possible, the biggest MSPAN is 32 kilobytes. So that's our the MSPANs. And it's important to understand that whenever you store a variable in Go, it's going to go to the MSPAN that can store that. So if you have a variable that is taking 26 bytes, it's going to go to the 32 bytes because the 24 bytes is not going to be able to store that. And so it's going to fall in the 32 bytes. In the previous example, we saw that we tried to store 8,200 bytes, and what happened is there's a span of 8 kilobytes, but the next span is 9,472 bytes. So that was the span that was used, that was the memory that is consumed. All the memory allocator have all these M-spans per size, per processor. Each processor have a main cache that points to all these M-spans of different sizes. And also there's a M-central that centralize all the M-spans of the same size. That is accessible from the M-heap. That is the main structure that manages the memory in the memory allocator. And if you have something that is bigger than 32 kilobytes, it's the M-heap who is going to take care of that and is going to reserve memory for that. It's going to take the pages that is needed and it's going to create that. So let's see an example of that. If you create, now we are creating 1 million of integers, well, 1024 multiplied by 1024 integers, that means 8 megabytes. If I do that, if I execute that benchmark, what I get is 8 megabytes plus 11 bytes for some metadata. But what happens if I add one more integer, 8 more bytes? It's going to take 8 megabytes plus 8 kilobytes plus 11. The 8 kilobytes is because the memory allocator, when it's allocating these big objects, the smallest chunk of memory that can use is a page. So it's going to take 8 kilobytes extra, even if I only need 8 bytes, because it's going to need another page. So that's about the memory allocator. I'm using all this, going through the process of initializing everything to explain you certain concepts of the runtime. But the memory allocator is not doing all this stuff. It's just generating all the M-spans, all that stuff, but it's empty at the beginning. So CPU flags. What are the CPU flags? The CPU flags are detecting the features on your CPU, the features that are supported in your CPU, the instruction sets and all that stuff, and setting some variables in the runtime for letting the rest of the runtime and the application know what is supported in this CPU. Then it's initializing the random numbers that is going to be for generating random numbers, and it's going to include the initialization of the seed. Also, the next step is the ICE algorithm. The ICE algorithm is supported in a lot of CPUs. A lot of CPUs have instruction sets for supporting ICE. And the idea is go use a lot ICE for generating hashes and things like that. So if the CPU supports that, it's going to use the CPU instructions. If not, it's going to use a generate a code-based hashing algorithm. Then the next one is interesting, is the main thread. The main thread is whenever you execute the binary, it's going to be executed in an operating system thread, in a process. And that operating system thread here gets assigned to the M-struct, and it's going to set up the M-struct with the operating system thread that is executing now, and it's your first M. And it's going to initialize that, set an ID for that, and it's going to add that to all M's struct, all M's global variable. Then it's going to initialize all the modules that are compiled with build mode, share, or plugin. Then it's going to initialize the GoArgs. The GoArgs is going to be initialized. It's going to take this AUXB information that we saw before, and it's going to put that in the args slice. It's a global variable in the runtime, and that arg slice is going to be exposed to the OS package through a function. So the OS package can access that, and you normally access the args through this method. The Go environment variable does something very similar, initialize the environment variables in a global variable in the runtime, and expose that to the syscall package, and the syscall package expose that to the OS package. Then we have the secure. Secure is going to take a flag that is set in the AUXB. The AUXB, apart from the environment variables and the args, have flags. And the secure flags is provided by the operating system when the binary execution needs to be especially careful about what it's doing because it can be insecure in some way. For example, if you have a set UID, that is going to be flagged by the operating system, like, hey, be careful with this because it can mean privilege escalation, things like that. So if the secure flag is set, the Go compiler is going to set to none the Go traceback. Doesn't matter what you put there, it's going to be set to none. Also, this was together in the 1.21, but now it's separated, the 1.21 and 1.22. There was in the 1.22 is separated part that is checking if the file descriptors are properly initialized. I mean the 0, 1, and 2 file descriptors are there and properly initialized. So you can tamper with it and generate other things. Generate other file descriptor that behave like the standard input, standard output, or standard error. Well, the debug environment is initialized here. It's using the Go debug environment variable and the debug compilation options to set some variables to know what debugging variables are, how we initialize the debug information in the runtime. Okay. Yeah, I know this talk is dense. It's a dense topic. It's not easy to digest. So take a big deep breath, and there's a kitten, so that's always relaxing, right? So, well, let's keep going. I promise that it's not too much more information, but still some. So let's keep going. At this point, we initialize the garbage collector structure. The initialized GC is going to basically configure the GC pacer and set the garbage collector to not sweep on the first iteration. So let me explain a bit more about the GC pacer and about the garbage collector. The garbage collector is composed by the garbage collector itself that is going to take care of all the mark and sweep phases and stop the world whenever it's needed in certain points of the garbage collection and all that stuff. That is done by the GC. There's a piece that is important that is the GC pacer. The GC pacer is deciding when the GC runs based on the memory consumption. You have this environment variable that is called GoGC. GoGC is it's normally by default is 100. That means 100%. That means the next garbage collection iteration is going to be whenever you double the memory, whenever you have 100% of the previous memory. For example, if you have 16 megabytes in memory, whenever you have 32 megabytes, it's going to pass the garbage collector and reduce that to, for example, 20. So the next garbage collection pass is going to be whenever it's 40 megabytes. That's the idea, is doubling after the amount of doubling the memory that was after the last garbage collection phase. Anyway, if you want to know more, in the reference I have a lot of stuff around the scheduler, around the GC pacer, about the garbage collector. There's a lot of reference that goes way deeper than what I can go here. So if you want to know more about the GC pacer, just check it out, the references. Another thing that is interesting that is going on with the garbage collector is the 4GC. The 4GC, it's a goroutine that is there, and it's going to be run whenever there is too much time without a GC phase, so it's with a GC pass. So it's going to force a GC pass. That 4GC is called by the system monitor. We are going to talk about the system monitor in a couple of minutes, but well. The other thing that is going to be there is the sweeper. The sweeper is another auxiliary process that is going to help with the sweeping process of the garbage collector. And the sweeper is auxiliary. That means that if you don't have the sweeper process, doesn't matter because the garbage collector is going to do the sweeping, but the sweeper process is there for taking advantage of idle processor that, well, okay, I don't have anything else to do, so I'm going to help with the garbage collector with the sweeping. And also you have the scavenger. The scavenger is the one that is actually freed in the memory. Whenever you, the garbage collector mark is not longer needed, but the one that is going to free memory and reduce the memory consumption and return the memory to the garbage to the operating system is the scavenger. Okay, that about garbage collection. Then we have the piece, the initialization of the piece, the initialization of the virtual CPUs. At this point, it's going to create 1 P per processor that you have in your system, or 1 P per the number of GoMax procs that you have defined. And it's going to create the structures and add that structures to the old piece. And then start the world. Now the scheduler is initialized. We have all the information that we need to start running goroutines. So the next step, what is going to be? It's going to be running a goroutine. It's going to run the initial goroutine that is going to run the function runtime main. The runtime main is going to do certain things that is actually the rest of the graph that you see here is the runtime main executing. So the runtime main, it's going to start initializing the system monitor. The system monitor is a process that is going to execute every 10 milliseconds and do certain things. Actually, it's not exactly 10 milliseconds. It's going to start executing every 20 microseconds, and it's going to start doubling after 1 millisecond, and whenever it reaches 10 milliseconds, it's stabilized in 10 milliseconds. But what is the system monitor doing? What's the responsibility of the system monitor? The system monitor is going to do some things. Every 10 milliseconds, it's going to run and start checking if there's something in the net pool that needs to be changed, that is already finished. The net pool is going to allow Go to do network requests in a way that it's more efficient. So it's delegating all the network requests to the net pool, and the goroutines gets waiting for the net pool to come back with the information. And the system monitor is going to check if the net pool has finished getting some data for some goroutines and reactivate that goroutines to allow them to run. Also, it's going to call the scavenger. It's going to wake up the scavenger time to time. It's going to force the GC if the garbage collector it's not run in a lot of time, it's going to force it. Also, it's going to detect long-running goroutines, and it's going to preempt them. So it's going to send operating system signal to the thread that is executing that goroutine to mark the goroutine as preempt, so the goroutine can end up preempting itself. Then also it's going to detect slow syscalls. The reason for that is whenever you have a syscall, you need to wait until the syscall. Well, syscall is a call to the operating system. Okay, whenever you have a syscall, the syscall is going to the operating system thread is going to wait until the syscall returns. So there's no way to do something else while you are waiting for the syscall. So what Go does here is very interesting. It detects that the syscall is slow, so the thread is blocked, and it's going to take that thread with that goroutine, put that aside from the current processor, virtual processor, and while that operating system thread is waiting, it's going to spawn another thread, associate that to the processor, and keep going with another goroutine. So this is part of the responsibility of the system monitor, detecting that slow syscalls to put them aside and allow the other goroutine to take advantage of that time. And also it's going to show some scheduler traces if you are enabling tracing. The enable GC, at this point, we enable the garbage collector, we spawn the sweeper, spawn the scavenger, and mark the garbage collector as enabled. That means that it's now safe to start running the garbage collector. So now we have the whole scheduler working, the memory allocator working, everything that we need working, so we can start running stuff. So the first thing that is going to run is all the inits of all the packages that are imported. And after that, it's going to start your main function and, of course, your code. So that is how the Go runtime initialized. But what happened while the Go runtime is running? While the Go runtime is running, you have a lot of things going on at the same time. You have the garbage collector that is going to be called time to time through the, well, whenever, for example, whenever you allocate more memory, that means that the memory allocator asks for more pages to the operating system. You are going to check the pacer, and if the pacer consider that, if the pacer says, hey, we need to run a garbage collection phase, it's going to be run, the garbage collector, or if the system monitor considers that the garbage collector needs to be run, it's going to run that. Also, the scheduler is actually not something that is going on. The scheduler is a chunk of code. That's interesting because you have goroutines that are working, and suddenly the goroutine has to wait for something, or the one goroutine finish, all that stuff. When a goroutine has to wait for something or has finished, it's going to stop itself, and it's going to call the scheduler code. So it's kind of the same operating system thread, the one that is transferred to that chunk of code that is going to select another goroutine to be executed. So the scheduler is not something that is monitoring. The scheduler is something that is called whenever it's needed. Also, the net pool is going to be there, the processor, the amps, all that stuff, all that structs are there in memory, and of course your code generating goroutines and generating things. Actually, some goroutines are not your code. For example, the system monitor, the scavenger are goroutines that are not your code. Also, as I said before, the compiler take advantage of the runtime being there. So a lot of things that is going to happen whenever you are executing your code is that your code is calling functions that are in the runtime. For example, whenever you are managing slices, maps, channels, all that stuff, whenever you are operating with that structures, basically what you are doing is calling the runtime code. Or whenever you spawn a goroutine, you are calling the runtime code. Or whenever you need to allocate more memory, it's calling the runtime code. So yeah, that's it. Let me summarize a bit. I'm going to go through the whole process quickly to refresh that. You run your binary. It's going to start with the thread local storage initialization. Then it's going to go to the args with the args be that from the operating system. It's going to start the operating system initialization with the number of CPUs, the size of the pages, then the scheduler, that is going to be a big process that starts with the stop the world, stopping everything, the stack spool, the memory allocator, all that gets initialized, the flags of the CPU are detected, the random number generation is initialized, the IS algorithm is detected if it's supporting your CPU, if not, use an alternative. You generate the first M based on wrapping your own the operating system thread that is running. You initialize the modules, you initialize the args, the environment variables, the secure flags with the go traceback set to none if it's needed, the debug information, the debug settings, start initializing the garbage collector with the pacer, initialize the processors, structs, and start the world, and then you run your first goroutine, that is the runtime main, that starts the system monitor, initialize the garbage collector, spawning the scavenger and the sweeper, and finally run the init functions and start your main function. Also, it's important one thing that I want to convey, and I think is important, is understanding the Go compiler works together with the runtime, and it's going to generate a lot of calls to the runtime for some syntax that you are using every single day. And also, I want to say that the illustrations of this talk are made by Juan de la Cruz from the Penpot team. They are Creative Commons 0, that means public domain, so they are mine, but also yours, so you can do whatever you want with them. You can download them in Penpot format. Penpot is an open source alternative to Figma, so you can check it out. Also, the references, as I said, there's a good article about the memory allocator. The garbage collector from Maya Roscrane, I think, was in GopherCon Israel or something like that. The GC Pacer from Mahat Gibrajani, that was in GopherCon US. The memory allocator from Andre Carvalho, NetPools, Cindy Shiradran, and the scheduler again from Mahat Gibrajani. That's are very good talks if you want to get deeper in any of these topics. All of them are very interesting. Also, if you want to see something else for me, I have the one about the Open compiler, that was the previous one, that has the same idea, a shallow overview of the whole process for compiling a Go file. And one about the goroutines and how the goroutines work under the hood. That is called The Secret Life of a Goroutine, so check it out if you are interested in that. Yeah, that's it. I know that it's a lot of content, it's a lot of field to cover, but I hope now you have a better understanding of what is the Go runtime, why it's there, and what are the different pieces that compose the Go runtime. But that is not exactly what I want. What I want with this talk is just to remind you that I'm a web developer, I'm a full stack developer, I write APIs and React applications. So I know all this because I dig into the source code of the Go compiler. So the Go compiler has something that is amazing, that is writing in Go. The Go compiler and the Go runtime is writing in Go. And Go, it feels like home almost everywhere. You go to any other project and you see a lot of patterns that are the same here and there, and all the styling is the same. That it makes easier to understand these kind of projects. Don't get me wrong, the Go runtime and the Go compiler is a very complex project. So that's complexity that you have to tackle if you go there, but still is a very well written, very well documented, and it's Go. So I will encourage you to go there, check it out, because if you are a curious person like me, you are going to enjoy it. So thank you. Okay, if you have questions, just remember that I'm a web developer, so it's...
Thanks for the presentation. I didn't understood what you explained about sysmod monitor when it put in a different thread syscall when they are taking too much time.
Okay, yeah. Let me try to explain that. I just rush almost everything because it's a lot of field to cover. But well, the thing is, whenever you have a syscall, this operating system thread is going to send the syscall to the operating system and wait until the syscall returns. A lot of syscall are really, really fast, but it's a syscall, it's too long, the thread is going to wait for that. So the thread is going to be blocked. There's no way that you can do any work with that. So what is going to, the Go compiler thinks, okay, the Go runtime thinks, okay, if this operating system thread is blocked, it means that I'm not consuming CPU, actually. I'm not doing anything with the CPU. So I can take that, deassociate that from the virtual CPU, so it's in other place, and in the virtual CPU I can schedule more goroutines with another operating system thread. So I'm going to spawn another operating system thread that is not blocked and put that in the processor. That way, This operating system thread here is kind of sleeping until it gets the return from the operating system. But I still have a throughput of, for example, if you have 8 CPUs, a throughput of 8 CPUs consuming CPU at the same time. So it helps with taking advantage of the whole set of CPUs that you have, because that thread is going to be blocked. So that thread is not going to do CPU work at that time. I don't know if that is answer your question.
Yes, that's clear. Thanks.
Thank you. Any other question? Okay. Thank you.
Okay.
Well, one quick thing. Yeah. If you want to approach me later and ask me questions or whatever, great. Also, I have some stickers from the illustration that you have here. So if you want some sticker, or if you want to ask me something, just approach me for the sticker and we can talk. So thank you.